The next topic is multiple continuous random variables. Thinking about two continuous random variables at the same time first. Right, let's start by two continuous random variables considered together. Just like we considered joint PMFs for multiple discrete random variables, we'll be able to consider joint PDFs for multiple continuous random variables. Okay, the two random variables defined for the same sample space, the same probability space actually, are said to be jointly continuous if there's a joint probability density function fxy such that for any subset of the two-dimensional real plane, the probability that x and y belong to this subset B is found by a double integral over this region B of the joint density function fxy of x and y, dx dy. Now fxy, x and y is a function of two variables, one corresponding to the values that the first random variable x takes, the other, the next one, y, script y, corresponding to the values that the random variable y takes. Let's consider the case when B is a rectangle. What is a rectangle? A rectangle in two dimensions is x1, x2, the interval x1, x2 cross the integral y1, y2. That's a rectangle. What am I talking about? I'm talking about this point x1 and point x2 versus point y1 and point y2. This is our rectangular region B. And the probability that x and y jointly take values in B is, as we said, a double integral over B, which is simply integral as x goes from x1 to x2 and y goes from y1 to y2, fxy, the joint density, dx dy. Any problem? You remember the double summation from the joint PMF case? This is simply an extension to the integral. Okay? So what happens when B is the entire real plane? Set B to the entire real plane R2. Then the probability that x and y are in R2 would be the integral from negative infinity to infinity in both directions, fxy, xy, dx dy, which should give you the value 1, because it's the probability that x and y take values in the whole real plane, which is an event of probability 1, by the way we defined random variables. So let's understand a little better what this joint PDF corresponds to. When I say the joint PDF at, for example, this point is fxy a comma b. Suppose this point has the x coordinates a and the y coordinate b. fxy a b. I could interpret this as a probability per unit area in the vicinity of this point. Okay? So the probability that x is around A and y, big X, the random variable y is around the value b is approximately equal to fxy a comma b times delta 1 times delta 2. What is delta 1 and delta 2? Let me magnify this figure right here, over here. This is my region, and this is my point, AB. And I'm thinking A2, A plus delta 1 is this strip, and B2, B plus delta 2 is this strip. So I'm talking about a small rectangle of sides delta 1 and delta 2. What is the area of this rectangle? Delta 1 times delta 2. So roughly, if you multiply the area of this rectangle by the density over that rectangle, of course the density is not going to be a constant over that rectangle, but as you make these distances infinitesimally small, you can approximate the density by a constant, roughly, and that gives you a volume. And if you take the volume over the whole region where x and y are distributed, you should find 1. But the volume over this infinitesimal rectangle is roughly proportional to the density. So you can think of the density as the probability per unit area. Okay? So basically we're going from 1 dimension to 2 dimensions. That's it. After you understand 2 dimensions, you can extend this easily to any number of dimensions. Of course, at this point, we won't be able to plot it anymore. All right. So just like the joint PMF, the joint PDF contains all possible information about the individual random variables in consideration and their dependencies. For example, we can find the marginal densities from the joint density. Let's find fx of x. Fx of x, remember, fx of x times delta is roughly the probability that x is around the value x. This can be found by integrating fxy xy over dy, over y. As y goes from negative infinity to infinity, if you integrate the joint density, you should find the marginal density of x. What is the explanation for this? Again, go from probabilities. Think in terms of probabilities. Fx of x times delta is roughly the probability that x is in x2, x plus delta. Okay? But you can find that probability by using the conditional, by using the total probability theorem again. How would you use that? You can find that by computing the probability that x is in this small region while y is in another region. Y is between y and y plus delta, and then sum over all such regions of y. Maybe integrate this over dy. What I'm writing here is not mathematical, it's intuitive. Okay? And the inside, this thing here is fxy, xy. Okay? So the reason for this identity is, again, the total probability theorem. You can find the marginal density by integrating the joint density over y. Just like we obtained the marginal PMF of a discrete random variable by summing the joint PMF over the other random variable. Okay? So, similarly, we can find Fy of y by integrating over x going from negative infinity to infinity in general, f xy over x. This is how we go from joint to marginal PDFs. Here's an example. Let's find the marginals from a given two-dimensional PDF. The joint PDF of the random variables x and y is equal to a constant on the set S sketched on the board, which I'm going to sketch in a minute. Find the value of the constant, the level, C, and the marginals of x and y. And also compute the expectation of x plus 2y. So here's the region that I'm going to propose. Not a very difficult one. So let's suppose this is the region over which the two random variables are distributed. Let this be 1, 2, and 3. And let this be 1, 2, and 3. This is x, this is y. This is the region over which the joint PDF is non-zero. And the joint PDF here on this region is constant, and it's equal to C. First of all, we are asked to determine the value of C. How do you think we can find the value of C? The integral of the joint density over the whole region has to equal what? 1. That we can use to determine the value of C. So the integral of C dx dy over the region S, this is the region S, has to be equal to 1. Okay? So what is C equal to? C is a constant height, right? You can think of this as a height sticking out of the board, a constant level sticking out of the board. And the volume of the whole figure has to be 1. Why? Because the volume represents the total probability. So C is then 1 over the area of S. What is the area of S? S, you can think of S as the two rectangles. One of them is 1 times 3, 3. The other is 1 times 2 is 2, so 5, right? So C is 1 over 5. Any questions? Anything? Oh, wait. Right, there's a problem in the way I marked this. So let's make this 1 and 2, 3 and 4. How about that? So this point is 1, 1. This point is 1, 2. This point is 2, 2. I sketched this a little fast. What? So the whole area, so this is okay, this is 2 and this is 2. Okay, so the total area is 4. You're right. The way I sketched this is really not up to scale, so that kind of tricked me as well. Maybe, shall I sketch this again? Let's sketch this again. Not a big deal. So 1, 2, 3, 4, and 1, 2, 3, 4. We have a point at 1, 1. So we have this rectangle. Now I forgot. Did it go? Huh? How about we make it go up to here? No? Okay. So that's the original figure I had in mind. And is this the figure? Oh, okay. Now it looks all right. This is the area S over which fxy, xy is equal to C. And the area of S is 3 plus 2. No, 2 plus 2, which is 4. Now, what are we asked to do? We are asked to find the marginals of x and y. How do we do that? Maybe we should think about that by inspection first. The random variable x takes values in which region? From 1 to 3. Is it more likely to take values from 1 to 2 or from 2 to 3? 2 to 3 it seems, because there is more volume. If you look at this figure, if you visualize this figure in 3 dimensions, there is more volume here than here. Okay? So we would expect, maybe let me make this smaller. We would expect, in fact, let me erase this. The marginal density of x to be bigger here and smaller here on this region. Now, between 1 and 2, we expect the marginal density to be uniform. Why? Because there is no reason it shouldn't be uniform. From 1 to 2, the joint density is uniform. So the marginal should be uniform at a particular level. We don't know that level yet. Let's think from 2 to 3. From 2 to 3, we're collecting 3 times the probability as here from 1 to 2. You see that? From 1 to 2, we have this much. I mean, the area, I mean, the volume under this region, over this region. From 2 to 3, we have the volume over this region. So this probability collected from 2 to 3 must be 3 times as the probability collected. So which should correspond to a height 3 times as big as this. Okay, so if this is A, this is 3A. And the whole integral, the area under this curve should be 1, which makes the value of A to be 1 over 4. Okay, so 1 over 4. I'm just thinking intuitively, remember. If this is seeming fuzzy to you, in a minute we'll really compute this using integrals. Let's also think about y. What do you think about y? Let me try to plot fy of y sort of sideways. Okay, this is y versus fy of y. Y is 1, y is 2, 3, and 4. Y lives between 1 and 4. Okay? Is it more likely to be between 1 and 2 or more likely to be 2 to 4? Equal. But this is a bigger interval. So what can you say about the height of the PDF? The height of the PDF at 1 to 2 must be bigger, because the total probability collected from 1 to 2 is equal to this volume, which is exactly equal to this volume. So we have a height that is, in this case, twice as big as this height. Let's compute these more precisely. Let's see, fx of x. What is fx of x? Fx of x is the integral over minus infinity to infinity fxy xy dy. Okay, this is what we started with. Now, fxy xy is equal to c, which is 1 over 4, when y, for a given x, when y is either between 1 and 2 or between 1 and 4, depending on the value of x. Let me use a colored marker. So if the value of x is here, between 1 and 2, then x and y take values in this square. Okay? When x is between 1 and 2, y is between 1 and 2. So we need to do this integral in two parts, in two cases. The first case is when x is between 1 and 2. When x is between 1 and 2, the integral is 1 over 4 dy. What are the limits of y? The limits of y go from 1 to 2. Right? Limits of 1 go from 1 to 2. When x is between 2 and 3, this time x is somewhere here, y goes from 1 to 4. Y goes from 1 to 4, 1 over 4 dy. So let's compute this. The density is equal to 1 over 4 when x is between 1 and 2, and it's equal to 3 over 4 when x is between 2 and 3. Exactly as we plotted it by intuition. Let me replot it. Fx of x is 1 over 4 when x is between 1 and 2, and 3 over 4 when x is between 2 and 3. Any questions? All right, I think now we can do fy of y easily. Fy of y is the integral from negative infinity to infinity fxy xy dx. Again, we have two regions. Let's use blue. When y is somewhere here between 1 and 2, x lives between 1 to 3. Let's do that. When y is between 1 and 2, the integral goes from 1 to 3, 1 over 4 dx. And when y lives between 2 to 4, the integral over x goes from 2 to 3, right? 1 over 4 dx. So it's 1 over 4 times 2, which is 1/2 when y is between 1 and 2, and 1 over 4 times 1, which is 1 over 4, when y is between 2 and 4, and our intuition was right once again. What was our intuition? Our intuition said we have twice the height here as we have here, which is clearly the case. Let me plot this. As a function of y, fy of y is equal to 1/2 when y is between 1 and 2, and between 2 and 4 it's 1 over 4. Any questions? So it's a little bit like looking at this three-dimensional figure and thinking of how much mass exists when you look at it from the x direction at every x. I'm sorry, when you look at it in the y direction at every x, how much mass per unit x exists? To get fx of x, and to get fy of y, similarly, at every y, you're looking at the x direction. Okay, what the next question was, compute the expectation of x plus 2y. Well, that's sort of a reminder of the fact that expectation is always linear. Expected value of x plus 2y is nothing but the expected value of x plus 2 times the expected value of y. This is true regardless of whether x and y are continuous or discrete, or neither continuous nor discrete, independent, dependent. This is always true because expectation is linear. So, what is the expectation of x? What is the expectation of x? We would need to compute the integral x times 1 over 4 dx from 1 to 2 plus from 2 to 3, we have x times 3 over 4 dx. Okay, and then add to this twice the expectation of y. Expectation of y will be, I guess, closer to 2 on the left of 2. And this will be from 1 to 2 y times 1 over 4, 1 over 2 dy plus from 2 to 4 y times 1 over 4 dy. And you can compute this as exercise. Any questions? So, what's next? Oh, so let me, since we are at the end of our hour already, let me quickly start by giving you the setup of this example, and we can continue to solve this example next hour, but I would like you to work out this example on your own as exercise first. So bear with me for one more minute. So x and y in this example are jointly uniform in a circular region of radius r. So this is r. And x and y are uniform. The question is asking you to find their marginals. X and y are jointly uniform. What does this mean? It's not explicitly stated in the question, so let me state it for you. fxy, xy is equal to a constant when x squared plus y squared is less than or equal to r squared, right? That's our region. And 0 otherwise. That's the problem setup. I have two questions to you. Number one, is x uniform by itself? No. Why not? Because when we look at a particular x, okay, if x is closer to the origin, it collects more probability. You know, remember, we're integrating over y. When x is right here, the density goes to 0. When x is over here, the density, the density, I'm sorry, when x is around here, the density is concentrated around x equals r. And when x is over here, more probability is collected. When x is right at 0, the density seems to make a peak. So I'd like you to compute this marginal of x. The marginal of y is by symmetry exactly the same. My second question to you is, what is the expectation of x times y? Expectation of x times y. What do you think? X times y is equally likely to take any positive value as any negative value, any corresponding negative value. So it's easy to see that the expected value of the product is 0. And the expectation of x is 0, and the expectation of y is 0. Also think, although we haven't defined it yet, and it's the topic of next time, whether x and y are independent or dependent. We'll talk about this in more detail next time.